Okay, so if you remember, we were looking at the angular momentum, and well, we basically first studied the formal theory of angular momentum about the rotational symmetry, the eigenvalues, eigenvectors, etc. And then eventually we were considering the radial Schrödinger equation for a particle in a radial potential. And the idea was basically we have this Hamiltonian, which is p squared over 2m plus some function of the distance only, so that the Hamiltonian and the angular momentum operator, they are just commuting. Now in this case, we were only looking at the orbital angular momentum, where J was defined as r cross p, just from classical physics. And we had seen that this definition of the rotations r cross p, they do rotate the coordinates. That is what they do, but this doesn't include the spin, in the sense that the eigenvalues are only integers. Now the thing that is missing in this r cross p is basically, we had seen that under this rotation, under rotation generated, well, let me just call this L. Under rotations, for example, around the z-axis by an angle theta, x, y, and z, this just becomes x prime, y prime, and z prime, where z prime is z, x prime is x cosine theta minus y sine theta, and y prime is y cosine theta plus x sine theta. So this operator only rotates the coordinates basically. But for example, if you look at some vector particle, so-called a particle with spin 1, you see if you are rotating this particle, let's say you have a vector at this point pointing in that direction. Now if you rotate it, that particle, that point becomes this point. So now that vector is now a vector at this point, but it's not this vector anymore. So you see, initially we have this vector, so if you just move the point, we should have this vector. So this is what this operator r cross p does. But under rotation, what we should do is this vector should also be rotated to this direction. So that is what basically the spin does. The angular momentum changes the point, physical point, from this point to this point without rotating the directions of my states. The spin just rotates the direction of the state, direction of the wave function. If it's a vector, its x, y, z coordinates should also change, not just the point at which we are evaluating it. It should be pointing in a different direction now. Spin is quite similar to a vector in that sense. Its spin also has a direction, and hence the direction of the spin should also change, not just the x, y, z. So that is what this r cross p operator is missing. And if we have an object that has a spin, we should add the operator that rotates the direction of the vector to this one also, to this r cross p, and that is in fact what we call the spin. And since the Hamiltonian, okay, any questions up to this point? And we know that since the Hamiltonian is rotating with these angular momentum operators, we know that the eigenvalues of the Hamiltonian are also eigenvalues of this angular momentum operator. And then the question was, what is this? We said that the eigenvectors were Lm. They might be pointing in some direction. The probability that this particle that has the quantum numbers L and M will be somewhere along the n direction. This is what we call YLM, the spherical harmonics. No, not just theta, theta and phi. And then, since our eigenstates should be an eigenstate of the angular momentum, I can just write, you see, the angular momentum operators, they only act act on the angles. They only change the angles. They don't change the length. So if I write a vector, if I write my wave function as a product of the radial distance and some function of the coordinates, let's say of theta and phi, this is the only part that is affected by the angular momentum. So that the radial part just acts like an overall coefficient. So as long as that part is an eigenvector, function of the angular momentum, my wave function is an eigenfunction of the angular momentum. And we already know what the eigenfunctions are. So let me just write r over here. So, and this n, theta and phi should be some y_lm. So that this state we have over here is now an eigenstate of our rotation matrices. And hence they are a candidate for my eigenstates of my Hamiltonian. Of course, what will determine whether this is an eigenstate or not is that function r, the radial part of my wave function. And then we said that if you just put this in our Hamiltonian, the Schrödinger equation just takes this form, minus h bar squared over 2m d squared by dr squared, the radial part, plus h bar squared over 2m L plus 1 plus the potential. Here I also have r squared. So this is now my eigenvalue equation. I need to solve this equation to obtain the eigenvalues of my states, of my system. And if you look at this one, this just looks like, at least, looks like the one-dimensional Schrödinger equation. So basically, using the rotational symmetry, what we have achieved is we have this three-dimensional system. We can describe this system as an effective one-dimensional system. Of course, this is not exactly a one-dimensional system, mainly because you see, one thing is this coordinate r can take values between 0 and infinity. So it is like a one-dimensional system with an infinite potential at the negative axis, in a sense. And the potential of this system, if we write some kind of an effective potential, this is h bar squared over 2m L plus 1 over r squared plus v of r. So we have this additional term, which basically behaves like this. So it diverges at r is equal to 0 and then goes to 0. This is 1 over r squared. So as long as v of r is not really more negative than minus some coefficient times r squared, so the effective potential is always positive at r is equal to 0. There is always a repulsion at r is equal to 0, which basically states that the particle cannot reach the point r is equal to 0. And then we also look, by considering our Schrödinger equation at small distances, we also said that this function r of r should go like r to the power L plus 1 as r goes to 0. Or our wave function to start with should go as r goes to 0, r to the L. Whatever the potential is, as long as it is not, it doesn't diverge faster than 1 over r squared, this should be how our wave function behaves, again, whatever the potential is. And this also tells us that the wave function at the origin should be 0, unless we are talking about L is equal to 0, which is called the S wave. So that is how this centrifugal barrier affects the wave functions. You see, in classical physics also, unless the angular momentum of the particle that you have is 0, it can never go to the 0 point, r equal to 0 point. It will just, if it's a bounce orbit, it just r changes between some minimum value and the maximum value. As I repeat, unless L is equal to 0. And this was where we had left, basically. Any questions? Now, let's look at some certain cases. Now, whatever system you have, you can always, as long as it's rotational symmetric, the eigenfunctions, you can always write them in terms of spherical harmonics. One possible example we can study is the free particle. Now, this is basically a rotational symmetric system. The potential is 0. And so again, the wave functions will be the radial part times YLM. And the radial part will satisfy this equation. Well, for L is equal to 0, the solution is kind of trivial. Of course, in this case, the energy of the particle is larger than 0. We can say that we can define the energy to be h bar squared k squared over 2m. So, for L is equal to 0, the equation we have is just minus h bar squared over 2m. The second derivative is equal to h bar squared over 2m times k squared times r, or r is just sine kr plus delta. But remember, our wave function is r over r. So if this is to be normalizable, this just tells me that this function has to be 0 at r is equal to 0. And this tells me that the radial part is just sine kr, the radial r function. And the wave function in this case, some normalization constant times sine kr over r. So this is our eigenstate with the eigenvalue h bar squared k squared over 2m. There is no restriction on the value of k, so the energy spectrum is continuous. Well, this is also what we already know when we use the Cartesian coordinate system for a free particle. It can have any energy. Now, of course, for L non-equal to 0, the equation is a bit more complicated, but the solutions are well known. They are almost the Bessel functions, spherical Bessel. So this function r is either r times the spherical Bessel function of the nth order, or r times the modified Bessel function NL. Are you familiar with the Bessel functions? Okay, fine. But you see, this function, let's call this R1, this is R2, R1, as r goes to 0, behaves like r to the L plus 1, whereas R2, as r goes to 0, it behaves like 1 over r to the L. So we had already seen that for small r, these are the two possible behavior for small r based on our differential equation. but only one of them is physically permissible, the first one, because the second one basically is not normalizable, to say the least. So we don't have a normalizable, the second solution is not normalizable, so our solutions are basically JL of R times YLM. Some coefficients that depends on L and M. Well, of course, then you can ask, okay, we already know the free particle, and we can say that the an alternative basis is just, let's say, psi k of R is e to the power I k dot R. But we already know that, okay, starting from quantum mechanics, let's say, we can just go from one basis to another basis. Both of them are bases, and so we can expand both of them in terms of each other. Well, this basically tells me that I can write e to the power I k R in terms of some coefficients times y L M theta and phi. And those coefficients I can even evaluate. This is equal to d cubed R e to the power I k dot R of theta and phi. Now if you evaluate this integral, you know the coefficient. This is called the partial wave expansion of the exponential. Now another interesting example would be particle inside a spherical well. Well, here we have particles localized in a certain region. In the free particle case, the particles were free to move everywhere they want. They can be anywhere. And from our general discussions on the quantization, if you remember, we had said that if the particle can be anywhere, again, the spectrum turns out to be continuous. Now, if you just localize it to a finite volume, then you will end up having a discrete spectrum. And in fact, if you just, this was our wave function, we can just use the previous case, the previous solution. The solutions are some normalizations. But of course, this time, we have a condition. The particle cannot be outside the sphere. So it should be the psi of R. When you evaluate that on the sphere, we have a hard, inside the hard sphere. This should be 0. This is our second boundary condition. Now, this tells me that well, sorry, just one correction here. This is not the JL of R, JL of KR. This is our solution. But this tells me JL of KA should be equal to 0. Well, the Bessel functions they will look like this one. The L is equal to 0 has a finite value at R is equal to 0, and it's just oscillating with a diminishing amplitude. This is L is equal to 0. For other L's, they start from origin, and again, they oscillate with a diminishing amplitude. Etc. So you see, the points where the Bessel functions are 0, they are not continuous. They become zeros at different points, depending on the value of L also. Well, this tells me that, first of all, Ka should only take discrete values. Let's say Ka should be equal to, let me denote it by epsilon and L. This is the nth zero of JL of x. So JL of the Bessel function will have infinitely many zeros, discrete zeros. The nth zero I just called it epsilon and L. So K can only take the values epsilon and L over A. So let me just call them K and L. And hence we have the discrete energy levels. And furthermore, since the epsilon and L's for each L in general they are different, there is no degeneracy in L. So for a given one, you see, the things to know. Epsilon and L doesn't depend on M. Different values of M basically have the same energy eigenvalue. Secondly, the energy values depend on the value of L. So different values of L, the total angular momentum quantum number, the energy values are different, in contrary to, for example, the hydrogen atom. In the case of the hydrogen atom, all the L values for a given N, they have the same energy. There is degeneracy in L also for a given N quantum number, but not in this case. Now, a third example that we can consider might be the spherical harmonic oscillator. In which case the Hamiltonian is p squared over 2m plus 1 over 2 m omega squared r squared, where here r squared is x squared plus y squared plus z squared. Well, we can write down the solution straight away in Cartesian coordinates. So it's the Hamiltonian basically can be written as the sum of 3 Hamiltonians, where hi is equal to 1 over 2m pi squared plus 1 over 2m omega squared xi squared. So this is our Hamiltonian. So in each direction, basically, we have a one-dimensional harmonic oscillator, and we have 3 of them. And we already know the energy spectrum. They depend on 3 quantum numbers, nx, ny, and z, for each direction. 1 quantum number for each direction. This is h bar omega, nx plus ny plus nz plus 3 over 2. Because for each direction we have 1/2, we have 3 directions, and so 3 over 2 h bar omega is the ground state energy. Well, you see, in the system we have a degeneracy. For example, if you say for energy is equal to h bar omega, let's say, even for 1 plus 3 over 2, you can write 1 as 1 plus 0 plus 0, or 0 plus 1 plus 0, or 0 plus 0 plus 1. So this is the nx value, the first number. The second number is the ny value. The third number is the nz value. So we have a threefold degeneracy for this first excited state. And for other excited states, you can just calculate the degeneracy similarly. So it's just given an integer, in how many different ways can you write it as sum of 3 different positive integers, non-negative integers. Now let's look at this problem from the rotational symmetric point of view. Again, we can just start by saying that psi will be equal to the radial component divided by r and ylm. Ylm is always there, since we have a spherical symmetric problem. And this radial function r will satisfy this equation. Now we already know that this function r should behave like r to the power l as r goes to 0. Now the thing is, how does it behave for, well, this v we already know. One over 2 n omega squared r squared. Now the second problem is, how does it behave in the other asymptotic limit when r goes to infinity? Now you see, when r goes to infinity, this term basically goes to 0. So we can just ignore that term. When r goes to infinity, this term becomes infinitely large. And hence the energy, we can just ignore the energy. So our radial function at infinity should satisfy this equation. This should be equal to 0, close to infinity. Or let's see, r double prime plus, well, 2's we can cancel, m omega over h bar squared, r squared times capital R should be equal to 0. And if we just look at this equation, this first term has the dimension of r over r squared. So this term should also have the same dimension. But that basically tells me that m omega over h bar squared should have some, let's call it a squared. A is some length scale of the problem. So if you write now r as a times x, x is not the x coordinate but some dimensionless, well, let me just call it u. Now r double prime, or d squared r by dr squared, this is 1 over a squared d squared r by du squared. So our equation becomes 1 over a squared d squared r by du squared. Sorry, this is a to the 4. You see, I already have this r squared over here. It should also first it should cancel its units, and then it will also give it a total unit of 1 over r squared. So I have to have 1 over length to the 4. Plus 1 over a to the 4, a squared u squared, r should be equal to 0. Well, I can just cancel this a's. So this is the equation that r should satisfy at infinity. Now, if u were constant, this was kind of an easy solution. It's just like the harmonic functions. U is not a function. U is not a constant. But nevertheless, we can say that r is equal to e to the power minus u squared over 2. Well, you see, this R doesn't satisfy my differential equation over there for an arbitrary U. But the difference, I mean, if we just put our R in our differential equation, let's see. R prime, this time derivative with respect to U, is minus U times R. R double prime is minus R plus minus U times the derivative of R, which is minus U times R. So here I have here there is a minus sign. So this is minus. You see, R double prime minus U squared R is equal to minus R. But since I'm considering the limit that U goes to infinity, this is negligible. So this basically tells me that this is the asymptotic form of my wave function as R goes to infinity. And now I know how my solution looks like. Psi of R is equal to R to the radial function over R. It is, well, the radial function looks like R to the power L plus 1 times e to the power minus R squared over 2a squared. This is the asymptotic form when R goes to 0. This is the asymptotic form when R goes to infinity times some function, which we don't know at the moment. And as long as that omega R doesn't diverge faster than e to the power R squared over 2a squared, this function will be normalizable. So that's the condition I have. That's the boundary condition I have to impose on this omega of R. And that would lead me to the quantization of the energy eigenvalues. Are you interested in deriving omega R? No, it will be basically first you obtain the differential equation for omega of R. Let me just write it down. Is U d squared omega by du squared plus twice L plus 1. No, sorry. Minus U squared d omega bar du plus lambda minus 2L plus 3 U omega. This is equal to 0. Where lambda is just related with the energy. Energy is h bar omega over 2 times lambda. And then what you do is you just make a series expansion of omega r to the power n, and then determine some recursion relation for an. So this is basically the recursion relation. We have a of n plus 2 is equal to 2n plus 2l plus 3 minus lambda divided by n plus 2, n plus 2l plus 3an. For very large n, an plus 2 is approximately 1 over n times an. But basically this tells me that if this is the case, omega r as r goes to infinity, it just behaves like e to the power r squared over a squared, and hence it diverges in general. So the only way to avoid this one, that the omega r just diverges faster than what my asymptotic form predicts, is that that expansion should terminate. But that also means that lambda should be equal to twice n plus L plus 3 for some, well, okay. So, or let me write it in a different form. And plus 3 for some integer n. And this integer n should of course be larger than L. And hence we have the energy condition. Energy was equal to 1 over 2 h bar omega lambda 1 over 2 h bar omega times 2n plus 3 h bar omega n plus 3 over 2. So you see, the energy eigenvalue depends only on this quantum number capital N. And the only restriction on this quantum number capital N is that n, well, let me put it larger than or equal to. N is larger than or equal to L. Or let's say L is less than or equal to N. So for N is equal to 1, we have L is equal to 1. Well, L is equal to 1 corresponds to M is equal to plus 1, M is equal to 0, M is equal to minus 1. So basically we have this threefold degeneracy that we had discovered also in the Cartesian case. Any questions? Let's give a 10-minute break now, and then we can continue.